Hi everyone, welcome to our reading group happening every Monday, and you can just join it as well if you want. Just come to our Zoom, and if you want to do that, all the information for that is down in the description. And now let's get to some video and discussion with Ahmed about his manifold diffusion fields paper.
Okay, so my name is Ahmed Elhag. I did the African Masters of Machine Intelligence, and I moved to Oxford recently to start my PhD with Michael Bernstein. This work on generative models for functions on manifolds has been done through a recent internship at the machine learning research team, with Yu Yang, Josh, and Miguel. I think we can start maybe. Yeah, I just want to thank you also for the invitation. It's a great pleasure to be here. I would like to start by a small recap or brief recap on diffusion models and also some key concepts on Riemannian manifolds. Maybe most of you have seen this multiple times, but just as a recap. So we have this idea of diffusion model is that you are given a finite number of samples, and then you would like to learn the distributions of these samples using normal distribution. So you convert your samples to Gaussian distributions by adding Gaussian noise for very large number of steps, and this is a forward process. And also you have a reverse process is that you want to sample from your normal distribution. So you want to sample the noise, and then you would like to reconstruct your signal. And here the neural networks comes. So the neural networks or the score network or also the denoising network is all the same. Is that you are given the noise, and then you would like to reconstruct the signal by predicting the noise in each step. So this is how you optimize your network, is that you predict the noise, and then you have the loss between your predicted noise and the original noise. So we can break this into three main components, as we discussed. You have the forward process, is that you destroy your input signal, and usually you have very large number of steps with a small amount of noise. And the reverse process, and then you have the denoising network. Okay, so another key idea about this work is that how you can represent your data as functions, which we also call it functional data representations. We know that we represent data as high-dimensional vectors or tensors. So how you can move from this representation to functional representation? Assume you have an image, for example. So we know the image can be considered as a vector in R times R W times H times 3. You have width and height, and you have some channels, maybe RGB colors. So the same image, you can consider it as a function going from R2 to R3. So going from XY coordinates or from a plane to the plane to R3 to RGB colors. Yes, directly saying like you assign RGB colors to your points in the 2D plane. In the same way, you have a 3D shape, for example, which is a tensor in R W times H times D times 4. You have XYZ coordinates, and also you have density. So for every point, and also you have colors. You can represent this shape as a function going from R3 to R4, from XYZ coordinates to RGB colors plus density. It's also like assigning RGB colors to every point in your shape. And also we can go forward in the case of video. You have a 2D video. This could be as a tensor in W times H times T times 3, which you can represent it as a function going from R3 to R3. So compare the video to the image, you only have a new dimension in the input space. So instead of R2, you have R3, which is the time. Then you have the same signal space, which is RGB colors. What is the main property of this is that this does not depend on the resolution of the signal. So for any signal or for any image, for example, you can have like different dimensions for your tensor, but you still have the same function. So it still is a function going from R2, from XY coordinates to R3. So this is the main property of this. Okay, so moving forward also, some concepts from manifolds, or what is Riemannian manifolds. I would like to make it as simple as possible. So a manifold is, you can think about it as some topological space that is locally Euclidean. It means that you have some neighborhoods in your points, but this is not the Euclidean distance. And what is a smooth manifold is just a manifold with a smooth structure or differentiable structure. So going a step forward, what is a Riemannian manifold is a smooth manifold, but you have some tangent space on your point. So for every point, you have a tangent space attached to that point, and then you can define the inner products in your tangent space. Okay, so on manifolds, we can define what is called the Laplace-Beltrami operator, which one of the main concepts in geometry processing. So what is the Laplace-Beltrami operator is a generalization of Laplace operator to functions defined on this Riemannian manifold. So assume you have a Riemannian manifold M, and then you have this eigenvalue problem, is that the Laplacian pi phi equal to lambda phi. So this eigenvalue problem define the eigenfunctions of the Laplace-Beltrami operator. So every eigenfunction is assigning a scalar to your points over the manifold M. And here, when you go from continuous setting to discrete setting, you have multiple choices. We'll come to this later. But the main point here is that we can say that these eigenfunctions can define orthonormal functional basis on your manifolds, which is also called or could be intrinsic coordinate systems. So after this, what is manifold diffusion fields, or what we are doing with Riemannian manifolds is that you would like to learn the distributions of functions, which is also continuous functions, defined on non-Euclidean domain. So you have a surface, and then you have a signal over this surface. So the main idea is to learn the distributions of these signals over your manifolds. And the main idea is to use this eigenfunctions of the Laplace-Beltrami operator as intrinsic coordinate systems. So for every point, you have a set of intrinsic coordinate systems or eigenvectors in Rk. And what is the main property of this representation is that it is robustness to rigid and isometric transformations. We know that the intrinsic property is invariant or doesn't change for rigid transformation, like any transformation in 3D, rotation or translations, or also reflections. But we also have isometric transformations. So for isometric transformations, it's defined as any transformation that keeps the geodesic distance between any 2 points constant. So it is the distance among the surface. We will come to this later as well. So let us go into our setting in manifold diffusion fields. What is our training data? So the training data is defined as functions. So functions over the manifold M. For example, in figure B, we have this is the famous or the standard Sanford bunny. And then you have a Gaussian mixture dataset on the surface of the bunny. So for every point, you define a signal in R. So, and this is our training data or training samples. Every sample is a function going from M to Y, from your manifold or the points of the manifold to a signal space in Y. And here, for example, compare this to images or 2D plane, is that you have a function going from R to Y, from XY coordinates to Y. And yeah, this is the idea. The idea is to use a generative models that can learn the distributions of these functions. Also citing some recent work on Riemannian generative models. For example, we have this figure C, is that you learn the distributions of points. So you can think about this as a one function. So you learn the distribution of points over the manifold instead of functions. So in our setting, this could be like a one function. Okay, so how we build this intrinsic local coordinate systems is that from the eigenvalue problem or the eigenvectors or eigenfunctions of the Laplacian. So here's some visualization for the eigenfunctions of the Stanford bunny. We know that also the eigenvectors is equivalent to Fourier positional embedding in the case of the 2D plane. So the main idea is that you order them by the lowest eigenvalues, and then you remove the first eigenvector, which is constant, and then you also normalize by the square root of your number of vertices or your number of nodes for graphs. These normalizations give you some robustness to the resolution of the mesh. So we will see later that you can train on some resolution, and then you can test or do inference at very high resolution. So you can go like up to 4 times resolution of the training mesh. So in this case setting also, which Laplacian to use, this depends on your choice. So if you have graphs, you can use the graph Laplacian or the normalized graph Laplacian, the famous one. Also, if you have meshes, you can use the cotangent Laplacian, or also if you have point clouds. So this depends on your setting. So you have the choice of the Laplacian you want. Okay, so how we feed this into a neural network, or how we parameterize a field. So the function or the field is equivalent in this setting. So we call it functions and we call it also fields. So for every field, we said before that our training data is samples, and samples are function on M. So for every sample, you have a function going from M to Rn. Assume your signal space in Rn. Maybe if you have RGB colors, it's R3. And then for M, you have like a vector in Rk for every vertex or every node. So you have going from Rk to Rn. And then you parameterize a field by a set of coordinate signal pairs. So you sample from this function a set of context and query pairs. And you sample like y and your signal y, and then you just stack them. And you also define a query set in the same way you sample from your function y and y. And here, this is the same setting of DDPM, the Nosing Diffusion Probabilistic Model, is that you define the forward process for your sampled context and query pairs. And the forward process here is that you destroy the signal, keeping the coordinate fixed. In other words, you don't add Gaussian noise to your coordinates. You just add noise to your signal space, which is Y. So here the training algorithm. You calculate your eigenvectors one time before training, and then you sample context and query pairs, and then you diffuse that. So that is it. This is the same setting of the DDPM. What you do at inference is that you define your query set, and then you do the denoising on your query sets. So returning back to the training algorithm is that you have context set and you have query set. So, and you have the forward process for both your context sets and your query sets. And in the reverse process, you diffuse the query sets. You are given a number of coordinates, and then you diffuse the signal on that coordinates. So let us continue here. We apply this to multiple geometries and data sets, starting from the wave geometry, and also the standard manifold, the sphere manifold. And we also have results on the Stanford bunny, and we lastly have graphs. So here are some results, the coverage and NMD using the MDF. We compare to Fourier positional embedding. So using the eigen-functions or the eigenvectors of the Laplacian, we are using the Fourier as a positional embedding. And here also some results on the Stanford bunny. Here's a sampling path on the wave geometry. What we are getting from this invariant representation of these eigenvectors of the Laplacian is that we know the eigenvectors are invariant to rigid and isometric transformation. So the idea here is that you train on one mesh and then you test on a transform mesh. Doesn't seem during training. So assume you have this cat and then you define a Gaussian data set on the POW, like you have a moving Gaussian, the POW, and then you have a moving Gaussian on the tail of the cat. And you just train on this. And you do inference at the transform cat. You can do like 3D rotation like this. Or you can do also isometric transformations. So you transform a cat, but you still have the geodesic distance between every point is constant. So here's the performance of MDF. You got high quality samples when you do this, but when you use Fourier as a positional embedding, this is totally false. So here's a plot, like you train on 0 rotation, and then you test on all these degrees. So MDF has a constant performance. So DBF is a way of, is not like they have this setting when you train on manifolds or something, but they have this the same idea of training like on images on functions. So you have an example, an image is considered from X to R2 to R3, from XY coordinates to R3. And then we build this setting. We consider it to compare with it as your positional embedding is a Fourier transform. But here you have the eigenvectors of the Laplacian. And here is to transform to high mesh resolutions, is that you train on a low resolution mesh, and then you test like a high resolution mesh, and you can go to 4x resolution, 4 times resolution. And here's the performance. So these are 2 experiment setting. The first one is that you train on high resolution mesh, and you also test on high resolution mesh. So this is the blue line. The orange line is you train on a low resolution mesh, and you test on high resolution mesh. So we know that the eigenvectors of the Laplacian has this property of preserving the structure of the manifold. So when you have like a very large number of eigenvectors, it means like you are getting a lot of details about your manifold. So that is why the gap increase between when you transform and when you train on the same mesh is that here the model getting like more details about the raw resolution mesh. So yeah, let us move to graphs, conformal paper or non-equivariant paper. So let us consider this problem. You are given the 2D graph and you would like to generate molecules in 3D. You are like to assign for every atom in your graph R3 coordinates, or for every atom or node, you would like to map it to R3. So we can formulate this problem at the same setting on meshes. You have a function going from M to Y. So the signal space in this case is R3 coordinates, XYZ coordinates, and the manifold is your graph. And this is also different from the previous setting, is that this means you can generalize to multiple manifolds or multiple graphs. So returning back here, during training, you have M is a fixed manifold, is a cat or a Stanford bunny or a wave geometry. So you have a fixed manifold. But here you have different graphs, and every graph can have different signals. So this is the setting here. And can do the same setting on what we did on meshes, is that you represent every point by the eigenfunctions or the eigenvectors of the graph Laplacian. And in this case, you have also node features or molecule features, which you can concatenate to your vector eigenvectors. And here some performance compared to the recent work on this. I think the torsional diffusion was a previous set of that. And here some comparison between using different number of eigenfunctions. We can notice like just using two eigenvectors, this give very well performance. And here some results, or some visual results. You are given these 2D molecules, and then you have different conformer. This is the real samples, and here our sample by MDF. I think this should be animation or something. Yeah, it's the sampling path. Okay, can return to the discussions. Let us conclude. We learned the distributions of continuous functions defined on Riemannian manifold. We generalize this to different geometries and dataset, and we use eigenvectors of the Laplace-Beltrami operator as a local coordinate systems or intrinsic coordinate systems, and then we formulate molecule conformer as functions on graphs. I have also a bunch of future directions if people are interested to consider this. So all of this about the data level. So there is nothing about the architecture. You can use any architecture for this setting. So the next question will be how you can design more efficient architecture rather than transformer or anything or receiver IO. And also MCF, which is called molecular conformal field, the one on graphs. This does not explicitly model the equivariance of the molecular system. So here we're still using the same architecture we have on meshes. This is not a GNN. And there is a lot of open direction here, like what if you combine this with equivariance architecture?
Okay.
And the last thing is that how you can use MDF to do molecule simulations or solving the forward and inverse problems of PDAs. There is also a small experiment in the paper. I didn't include it here, but maybe people, if interested, can look about it. Is that so? In the case of let us take maybe this example or any example. In the case of BDE, assume you would like to define the heat equation over this geometry. So you just have a new dimension in the input space for the time. So you have M times R going to R. So you still can use the same setting, have this input space, and then you have also output space. So for molecular simulations, you have a new dimension also in the input space. So this is how you can think about the time dimension. Yeah, I think this is all I have. Maybe can open.
Then thank you very much, Ahmed, and thanks for answering so many questions already. So in the chat, we have the question how this thing works for molecular graphs, and yeah, maybe there we can give the hint that there's a whole paper about this called molecular conformal fields, also from the same group, and there they basically you now have the same thing as in manifolds, but now your positional encoding is no longer given by the eigenvectors of the Laplace operator on some manifold. It is now just your positional encoding is positional encoding on a graph, and you can use different things, I guess, but they use the Laplace or the graph Laplacians eigenvectors. Is that accurate, Ahmed?
Yeah, so that paper also has some more analysis about more data set, but I think the core problem is the same.